Dear students, let us continue our video lectures on Advanced Digital Signal Processing course. Let me share the screen. Let us continue our discussion on frequency domain analysis of systems. We have seen in the previous video lecture how the systems can be classified based on the frequency response of the systems. That is, which frequencies do they attenuate and which frequencies do they pass. That is low pass filters in terms of filters. Explicitly discussed about low pass filter and high pass filter. Okay, and there is another filter called band pass filter, which will pass only a band of frequencies between say 0 to pi, you can say, or minus pi to pi. And we have also discussed about the inverse systems for the given system. We have seen with a couple of examples how to identify or how to find the inverse system given the transfer function or the system function. We can find inverse system by 1 by the transfer function 1 by h of z. We have also seen how to find the ROC for the inverse system, okay, given the ROC for the original system. Okay, considering that there should be an overlap between the ROC of the h of z and hi of z, so that there is a common region wherein which we can have this relation, okay, or this relation. Okay, so and we have seen two different examples. One in which we can see that the inverse system can also be causal and stable, okay, or the and just like the original system. But in some other example, in another example, we have seen that the original system may be causal and stable, but the inverse system can be causal but not stable, or stable but not causal. Okay, so if the original system is causal and stable and the inverse system is also causal and stable, we said such systems as minimum phase systems, and they have some significance, and we have given an example of their significance. What is that? So if we have a communication channel and if you want to design an inverse system, we would wish to have a inverse system that has causal and stable, okay, that has the nature of causality and stability, so that it is realizable and as well as it is controllable, right? And we will see now few more examples, okay, for inverse systems, and also we will see a general discussion on inverse systems and minimum phase systems. We will also introduce another class of systems called all pass systems, okay, in this video lecture. So a general h of z or a general system can be represented as, okay, in terms of the poles and zeros. Okay, let me put it here. One. Okay. So if we see before, we have defined this slightly differently in terms of AK and BK. Okay. So here we are defining it as in terms of CK and DK. The relation between them is, see, in the previous discussions, we have defined h of z as sigma BK z power minus k equal to 1 to m or 0 to m 1 minus ak z power minus k equal to 1 to n. Okay, So this can be considered as A naught. Okay, if it is not 1, then this can be considered as A naught. Okay, so this, when we just do a little bit of simplification, this can be written, okay, this can be written equivalently in this form, wherein we B naught by A naught, we will write here, okay, and then this is like the numerator polynomial is decomposed into different factors, okay, each is giving 1 0 of this h of z, okay, and the product of all these terms will give us the numerator polynomial which we have seen there, okay. Similarly, the denominator polynomial can also be decomposed in terms of the roots or the poles, okay, and this gives rise, the product of all this gives rise the denominator polynomial, okay. So these are roughly the equivalent and general representations for the system function or the transfer function, okay. H of z transfer in pole 0 form, okay. You can consider this as pole 0 form because we can easily see or readily see what are the poles and zeros here from here, okay. Now see, if this is the system, assume that the system H of z is causal, okay, and if I say if it is causal, it means that the ROC is what? What can you comment about ROC? If I say that H of z is causal, ROC is mod z greater than what? See, this is the H of z, that is the system function, okay. X of n is input and y of n is output, okay, and for which this is what is the transfer function of the system, okay. And if I say that this is causal system, then what should happen to the ROC? It should be the outside of the outermost pole, okay. Where is the pole now? What is the outermost pole for H of z? It is maximum of, it is a maximum of ck for all k, right? So mod z is greater than or like greater than maximum of ck. This mean by causal. And if we say that the H of z is stable also, causal, okay, and stable, what does it imply? It implies that the maximum of, okay, condition 1, okay, 1 and, okay, well, there is another condition that we can put now, maximum of ck has to be less than 1, okay, so that the maximum value of the pole itself is less than inside the unit circle, and the ROC extends from that pole, and hence the ROC includes unit circle, okay, and outside of the like outermost pole, okay. So this is what is implied, right? So this, I hope you are able to understand and relate from the given H of z. Now, if we want to comment something on the inverse system, what is Hi of z? How do I write Hi of z first of all? Okay, this form is simple for us to write, okay, Hi of z into 1 to n, okay. Please note that this we can start from 0, okay. 1 to n, 1 minus ck z inverse, because it's inverse, okay, 1 by H of z, 1 minus dk z inverse, okay. See, now if H of z has to be causal and stable, see, is there a possibility that Hi of z is also causal? The answer is yes, because there can be, say, if there is a overlapping region of convergence, H of z ROC like that is good enough for Hi of z, okay. So Hi of z ROC will have overlapping region, so it is possible that dk is Okay, the HI of Z is also causal. HI of Z is causal implies that, okay, what should happen? Mod Z, the ROC is mod Z greater than maximum of decay. Okay, and HI of Z being, okay, causal and stable, should imply what? Mod Z, okay, condition 1, this let it be condition 2 here, condition 2, and what else? Maximum of K, dk has to be less than 1. Okay, so in a sense, if you wish to tell H of Z and HI of Z both are to be causal and stable, if and only if, okay, when they are both causal and stable, if and only if what? All, see, dk now, whatever you are seeing as dk now, were there even in the, whichever you are seeing as dk now, are there even in the H of Z as what? Even in the H of Z as zeros. Okay, so and hence, so you can tell directly from H of Z when both H of Z and HI of Z are causal and stable. When can you tell? Its poles are less than 1, all maximum of the pole. In fact, all the poles are less than 1. Maximum is less than 1 means all the poles are less than 1, as well as the zeros of it are also less than 1. Okay, so and the ROC is outside of the outermost pole, and subsequently follows that ROC is outside of the outermost pole of subsequent 0 for the inverse system. If and only if, mainly the criteria that is needed is, okay, maximum of K, Ck and maximum of, I will write in words here. Okay, so to complete the discussion, all poles and zeros inside the unit circle. Okay, if and only if all the poles and zeros, okay, of what? Of H of Z, okay, are inside the unit circle, and the ROC extends outside the outermost pole for the H of Z. Okay, right. So this gives a guideline on when the system can be minimum phase, because this property is for minimum phase system. Okay, for a minimum phase system, we see that all the poles and zeros are inside the unit circle. Okay. Okay, this is the property of the minimum phase system. Okay, so let's now leave the discussion here on the inverse system and minimum phase system. We will subsequently follow up this discussion when we discuss about the alpha system and decomposing any of the system into minimum phase system. We see some very useful properties of the minimum phase system in addition to what we have seen here of having causal and stable inverse. Okay, we will see another couple of properties, and then we will also discuss how to decompose any system into a minimum phase system and all pass system. Okay, and we see the need as well. Okay, so now let us define, before the discussion, any further discussion on minimum phase system. Now let us define all pass system. What do you think is all pass system? As the name indicates, it passes all the frequencies. Okay, so to pass all the frequencies, its magnitude spectrum has to be 1 for all Z. Okay, so let me define it. Okay, this is a typical definition. If we write in terms of h of e power j omega, C is a complex number. Okay, complex constant you can say. Okay, so this we are saying it is all pass system. Okay, let me show how this is all pass system. See, first, before we discuss on the magnitude response, how do we find magnitude response of a given system? Let us define, how do I find h of z? Usually magnitude response is defined as whole square. Okay, or h of e power j omega whole square. This is the magnitude response of a system. Frequency like this can be expanded as h of e power j omega into h star e power j omega. Okay, so for any complex number, this is how we write the magnitude, right? So this into dot star, in fact, no? So element by element multiplication at all omega. Okay, now given this, we can see now whether this is if we find the magnitude response for this given definition, will it be 1 for all omega or not? We will check. So we will also define in terms of h of z. How do we define the magnitude response? H of z here into h star will come 1 by z star. Okay, so because there is r term here in the h of z, there will be 1 by r term here, but nevertheless there is a like it has to be like star complex conjugate for h as well as in z. Okay, so now let us take the this definition. Okay, definition 1. Okay, to check, verify with this system. System 1 and definition 1. Okay, so let us see if the what is the magnitude response of the given system definition. Okay, so now h of e power j omega. Please note that whatever I have written here, h of z and h of e power j omega are of the same system. Okay, except that the it is represented in frequency like e power j omega, that is in discrete time Fourier transform. This is represented in z transform. Okay, for the same system. Okay, so now let us see. So h of e power j omega, that is e power minus j omega minus c star by 1 minus c e power minus j omega into h star of e power j omega. So it is e power j omega. I am directly writing the h star c by 1 minus c star e power j omega. Okay, right? And this is now, let us do one small algebraic tricks. So let us take e power minus j omega out. Okay, from the first term, e power minus j omega, if I take out, what do I get? 1 minus c star into e power minus j omega, sorry, plus j omega by, from denominator also, let us take e power minus j omega out. Okay, e power j omega minus c. Okay, And let us write the next E, like the second term. Now see if any of the terms are getting cancelled. You can see that, okay, this gets cancelled with this. Okay, similarly, this gets cancelled with this. Okay, and hence anyway this and this gets cancelled. Okay, so you have this equal to 1. That means for all omega, please note that. Okay, so the magnitude response of the system, if we define the system response like this, is 1 for all omega. Okay, so what does it mean? It means that the given system now, so if this is the system which is defined with this h of e power j omega, okay, x of n and out y of n, okay, it passes frequencies, okay, without any change, any attenuation, okay, any change. Okay, that means in the frequency domain, if we sketch, okay, if we sketch in frequency domain, if we assume that this is 0 and this is minus pi and this is pi, okay, then the spectrum for this is all 1. Okay, this is spectrum for what? For what did I sketch the spectrum here? Okay, please note that this repeats from minus pi to pi. So the spectrum is all flat, we say. And then this is h of this for what? What is defined for what? H of e power j omega. Okay, magnitude mod. So here we are not bothering about the frequency. Okay, we have just analyzed how will be the magnitude response of the all pass system. Okay, now we will have a small discussion on the frequency response or the phase response as well. Now, when we consider frequency response, there are two terms. One is the magnitude response and another is phase response. Okay, what we have discussed and analyzed here is phase response. Sorry, magnitude response. Okay, what we have analyzed here is magnitude response of the all pass system. Okay, so now let us see a little bit on the phase response. Okay, there we will even after a couple of discussions, we will define some things as well. Okay, see, we will discuss phase response of the all pass systems. But before that, let me discuss what is phase response. And say, assume that you have, this is not an all pass system, but assume that h of e power j omega is given as e power minus j omega nd. Have you seen this system any time before? This is what system? Delay system. Because in time domain, if you see, h of n is equal to delta of n minus n naught nd. Okay, it delays the like input signal. If you take any input signal x of n and give it to this system defined by this frequency response or this impulse response, what it does, the output you get is x of n minus nd. Okay, this is output. So this is referred to as delay system. Okay, now this system, let us just understand what is phase response and then apply for the all pass systems. So what is phase response? Phase response is angle of h of e power j omega. How do we define it? Angle of this, if you want. Okay, so you can write this as cos omega nd minus j sine omega nd. Okay, so if we write angle, so we want to write the angle, we are writing like this. Okay, h of e power j omega, and then we write the angle. Now we have written h of e power j omega, and then now we write the angle. What is the angle? Tan inverse of, for any complex quantity, the phase is defined or given by minus sine omega nd by cos omega nd. Okay, and this is given by, this is also tan, so minus omega nd. Okay, this is the continuous phase. Okay, because see, usually tan inverse gives the wrapped phase. Okay, so you will get the phase only in the range minus pi to pi. However, whatever I have written here is absolute phase or continuous phase. Okay, so this is, see, if you sketch this, how will it look like? This continuous phase for this example. How does it look like? So it is with negative slope and with a slope of omega nd. Okay, so here nd is a constant and omega is anyway axis. Okay, this is omega axis. So if it is positive slope, it would have been something like this. Since it is negative slope, it looks something like this. Okay, this slope is given by omega nd. Okay, and this is minus omega nd. So you can, from here it is, okay, omega nd. Since I have written in negative direction, it is minus omega nd. Okay, so this you can consider. Okay. Okay. Or rather, we can write this more effectively here. Okay, this is minus omega nd. Okay, this is 0. Okay, so now you can see that this is the phase phi of omega. We can just, for ease of notation, we can denote this as phi of omega. This is the phase of a frequency response. Okay, this is how we find the phase, and this is the phase of the frequency response of this delay system. Okay, now there is another term that is worth defining here, that is referred to as group delay. Okay, and before we define the group delay, let us see the nature of this phase phi of omega. How is it looking? Is this linear in omega? The answer is yes, and hence it is referred to as linear phase. Okay, the system having this kind of phase response is referred to as linear phase system. Okay, linear phase. Okay, this is linear phase because it is linear in omega. Okay, because omega is the axis on which we plot this phase response. Phi of omega is linear in omega. Okay, please note that. Fine. So linear phase is known to have some good properties. One easy and clear property you can see is, see if there is a linear phase in the system, what it does, it only introduces a delay in the signal, no other modification to the input signal. That's a very desirable characteristic. Okay, in some cases, in some of the cases, we don't want to modify the signal. Okay, at the maximum, we could allow only the delay in the, because of the filter that we design or because of any system that we introduce. We don't want to change the phase response. We only want to modify the magnitude response. Okay, ideally it is not possible to only modify the magnitude response. There should be some modification need to be done for the phase as well, but in the worst case, we will allow to have a delay in the phase, in the signal, that is only having linear phase. Okay, so wherever we want to do some modification to the frequency, magnitude of the frequency response through a filter or a system for the input signal or the like input sequence, what we can allow is to have a linear phase, okay, in the phase response, and hence a delay in the output signal compared to input signal. And the magnitude response we may modify based on our convenience or demanded by the system. Okay, so having linear phase is most of the times a desirable quantity. So if we, what is the other possibility? We may have a non-linear phase. Okay, if there is a non-linear phase here, okay, because this omega nd is not linear function of omega for phi of omega, then that what will happen? It doesn't only delay it. There will be some changes in the signal as well because of the phase term. Okay, which is not usually uh, good, or which is not usually encouraged for the design of the filters and some systems. Okay, so having linear phase response is desirable. Okay, so to capture the same, we more effectively, there is another term that is usually used, that is referred to as group delay. What is group delay? Is, say, we can denote this group delay with tau of phi, and this group delay is defined as d by d omega differentiation of phase response is group delay with negative sign. Okay, minus d by d omega of phi of omega. This is referred to as group delay, phase response and group delay. These are two important terms that we use in the frequency domain analysis of the systems. Okay, and now in this case, what is tau phi? Minus d by d omega of minus omega nd, and hence this is equal to nd. So constant. Okay, the systems with constant group delay, okay, are preferred because they will not introduce any of the distortions due to the phase term. Okay, because group delay is only dependent upon phase term. Okay, so this is also any linear phase system has constant group delay. Okay, can you figure out any other system having constant group delay? Can you figure out any other system? Okay, phi of h of e power j omega, can you give any other h of e power j omega that has constant group delay? Okay, can you define it? So what we can see is minus omega nd plus some constant if I put. Okay, so then r n naught I can put. So any like omega naught if I put, then what will have to happen? So this implies this also for this as well. Okay, tau phi is equal to what? For constant anyway 0 and d. Okay, so this is also fine. This is referred to as generalized linear phase. See, whatever we have here is linear phase. Whatever I have seen here is generalized linear phase. That is what? H of e power j omega. I will directly write the system here. E power minus j omega nd plus some omega naught. Okay, so this is generalized linear phase system. Okay, so wherein this, if you want to write it, this can be written as e power minus j omega naught into e power minus j omega nd. Okay, this is generalized linear phase system, wherein the constant term is introducing a small phase. Okay, there may be a constant term in the frequency response, that is which is complex number, complex constant, and that is introducing the phase. So as I said, the systems having constant group delay, okay, are preferred for like avoiding any distortion due to the frequency response. Avoiding any distortion due to the phase phase response introducing in the processing. Okay, systems with constant group delay or linear phase are preferred as phase response do not introduce any distortion during frequency domain modifications to the or processing of input signals. Okay, they at the max only introduce the delay. Okay, fine. So thus these are more preferred for practical like applications, especially in filter design. Okay, fine. So now let us see how will be the phase response for the all pass system. Okay, so what is the all pass system? How is general all pass system defined? Let us take this itself for ease of understanding. Right. So how do I write angle of h of e power system? Let us directly write what is the phase response of the system. So to write the phase response, we define C to be R e power j theta. Okay, and C star hence will be equal to R e power minus j theta. Okay, and given this, after substitution and simplification, you can see that angle of h of p per j omega is equal to that is phi of omega is equal to minus omega minus 2 times tan inverse of r sine omega minus theta and 1 minus r cos okay omega minus theta. We skip here the simplification from here to here. Okay, so with substitution of this in this and with further simplification, algebraic simplifications will enable us to write in this form. Okay, I will skip the simplification now. Let us see some of the properties of this, because these will have some consequences in the subsequent discussions. Okay, so see, and let us also write now group delay, which is also an important term. Group delay which is d minus d by d omega times phi of omega. Okay, can be written. This also I will not give the simplification here, but you can refer the textbook for simplification. Okay, there is a reasonable algebraic manipulations that are required to get this. One minus r square by the inferences are very important. So I am skipping the simplification for simplicity and directly getting into the inferences. 2r cos omega minus theta. See, we will if we analyze the group delay, what do you think? Say if mod r is less than 1, that is mod r is less than 1 for a see if mod r is less than 1, what does it mean? The poles are inside the unit circle. Okay, and hence the zeros are also inside the unit circle for an all pass system. Okay, And if for a causal alpha system, the ROC is outside the like mod R, okay, circle defined by R, and the it includes unit circle as well. Okay, if mod R is less than 1. So this is for a causal and stable system. This stable alpha system. Okay, so for this case, tau of omega, you can see that R is anyway less than 1, and hence this is numerator is positive. Okay, what about the denominator? 1 plus R square minus cos. Okay, so since R is less than 1, this is anyway, this term is less than 1. So 1 minus R. So if you see 1 minus R cos, okay, omega minus theta, this whole thing is whatever it may be is positive. Okay, plus R square, this is anyway positive. Okay, and hence if mod R is less than 1, irrespective of the sign of R, the whole thing is positive. Okay, so the group delay is positive for an alpha system. That implies group delay is positive for any stable alpha system. Okay, and what about the phase response? What about the, say, phase response? Phi of omega, usually if we give group delay, how is it defined? Is integral of tau of omega, because this is defined as differential, okay, d omega minus times plus phi of omega naught. Okay, so now see, if this is positive, then what we could conclude is that phi of 0, you can say here. Okay, if this is positive, what we can conclude is, see, the first term in this is, if this is positive, then first term is integral anyway of a positive quantity is a positive term, and hence the with a negative sign it is, so the whole thing is negative. Okay, and phi naught, if you substitute 0 here, okay, so what you see is, okay, or this 0, so whole thing is 0. So whole thing phi of omega, this implies that phi of omega is negative. That is, phase response is negative for a alpha system. Okay, alpha system with, okay, mod R less than 1, that is stable. Stable alpha system. Okay, having all poles less inside the unit circle will have okay, negative phase response. Okay, so always phi of omega is less than 0. Okay, and the group delay, if we see, tau of omega is greater than 0. Okay, these are good properties of an alpha system. Okay, we will see the implication of these properties in the discussion now. So now let us bring in what is the importance of this alpha discussion of alpha system, minimum phase system, and so on. And to put these together, let us discuss the magnitude response. So of a, how many possible magnitude response are can be there for a given pole zero plot. Okay, and then we will see for all among all the possible magnitude response of a given system, among all possible systems having same magnitude response, which of the system is preferred. Okay, so let us position our discussion with the given pole zero plots. Let us take an example and proceed on this. Okay, So let us assume that we have actually a pole here, okay, and another pole here, okay, 2 poles and a 0 here, okay. So what is the system? So the poles are at 0.8 into e power j pi by 4, the first pole location. Second pole location is 0.8 e power minus j pi by 4, okay, and 0 location is half, minus half, okay. And hence h of z, now if I want to write for this, okay, given pole 0 plot, we want to see how many possible systems can be written with same magnitude response. Pole 0 plot to magnitude response. Okay, so h of z, how can we write? 1 plus half into z inverse by 1 minus 0.8 into e power j pi by 4 z inverse into 1 minus 0.8 e power minus j pi by 4 into z inverse, right? So we just for like completeness add one more pole so that our discussion so this is on this side z inverse, okay. So first of all, let us note that is the system stable and causal? Can the system be both stable and causal? Okay, so the last pole that we have put made it not to be stable. Okay, need not be stable. Otherwise, it is stable and causal. So to so to make a causal and stable system, let us avoid now then the last pole. Okay, so this is the stable and causal system. This can be a stable and causal system. Okay, if like its ROC is mod z greater than 0.8, okay, then the system is h of z is stable and causal. But is this only possible system having this pole 0 plot? Okay, right, the other possible system with this pole 0 plot is mod z can be less than 0.8, okay, and then h of z is not stable and not stable as not causal as well. Okay, now the question is, are there any other systems having the same magnitude response as system 1? Okay, so let me directly write another possible system having same magnitude response. Okay, I will write here and you verify. So assume that I will put zeros. Okay, so of and zeros and poles of that system. Okay, so this is 1 by 0.8 e power minus j pi by 4. Okay, and then this is my 1 by 0.8 e power j pi by 4. Okay, the location of pole I am putting here, and this is 2. See, now if I write h of z is equal to 1 plus 2z inverse by 1 minus 1 by 0.8 e power minus j pi by 4 z inverse into 1 minus 1 by 0.8 e power my j pi by 4 into z inverse. See, for each of this system 1 and system 2, let us write the magnitude response. So let us define C1 magnitude response, okay, of Z as H of Z into H star of 1 by Z inverse, as we have previously seen. Similarly, H1, let this be H1, okay, and let this be H2, and hence we write C2 of Z to be equal to, so we will write somewhere, so C2 of Z to be equal to 1 by H2 of Z into H2 star of 1 by Z star. Okay, so now let us simplify either of this, and in fact both of these, and if we simplify, you see that C1 of Z equal to C2 of Z. That means both of them have the same magnitude response. Okay, so to do that, let us write simply here H1 star of 1 by Z1 star. Okay, Z star. Let us write this. See, if I write this, what is this? 1 plus star and star 1 by 2. Okay, Z, because 1 by Z and star will happen by 1 minus 0.8 e power j pi by 4 into Z again. Okay, and into 1 minus, see here, I'm writing Z star, okay, whole star, 1 by Z star. So there will be a minus sign here for the first term, e power, sorry, 0.8 e power j pi by 4 into Z here. Okay, so the positive sign here became negative. Okay, negative sign here became positive. Please note that. And Z star, Z inverse became Z here. Okay, and star also should be there. But star and star, these two stars get cancelled and Z only will be here. Okay, even here. So please note that. Now, given this and this, okay, let us see if there is any like both are same or not in terms of mainly magnitude response. Let us take Z square out from the outside. Okay, Z out. So Z inverse into 1 plus 1 by 2 Z inverse. Okay, divided by, here also let us take, let Z square outside, 1 minus 0.8 e power minus j pi by 4 into Z inverse. Okay, into 1 minus 0.8 e power j pi by 4 into Z inverse. Okay, I have taken Z square out from the numerator and denominator. So I have written this. Now if you see H2 of Z and this, compare H2 of Z, okay, and this one, is there any similarity you are able to find? This whatever we have written here is exactly what? Is exactly equal to Z inverse into H2 of Z. Okay, so and hence when I find the magnitude response, okay, what will happen? Both are okay. So Z anyway, mod Z is are here. Okay, but I assume that if we especially take in the frequency response, okay, they are exactly same. Or to knock off this Z term as well, if we have something like a sorry, oh sorry. Okay, just a minute. When we write this, so what you have here is Z inverse into H2. Similarly, when you see now H2, similarly H2 of star of 1 by Z star here. Okay, what you see is, okay, H1 of Z, okay, H1 of Z into Z inverse. Okay, and hence now, if you write C1 of Z, what you have is H1 of Z into H2 of Z into Z inverse. Okay, Similarly, C1 of Z, if you write, it is also equal to H2 of Z into H1 of Z into Z inverse. Okay, and hence you can see that the magnitude responses of both of the systems 1 and 2 are exactly same. Okay, and thus you can see that there are not more than one possibility for having the systems with same magnitude response. Okay, for a given magnet, like systems with having same magnitude response. Okay, and their pole and zero locations has some relation. Okay, here how are the poles and zeros related? You can see that the any of the pole is related or zero is related by, okay, 1 by Z star. Okay, so you can create the systems having poles and zeros, okay, Z and at Z and 1 by Z star, okay, will have the same magnitude response. Okay, so now you can see that as in a summary, both system 1 and system 2 have same magnitude response. Okay, and how many such possible systems for a given 4-0 plot are there? That we will see now next. See, if I give you a simple case, initially with okay, this is being point half. Okay, only if h of z is this 1 minus half z inverse. Is there any other system having same magnitude response? The answer is yes. That is h of z, h1 of z, let be this, h2 of z having 1 minus 2 z inverse also have the same magnitude response. Okay, so the systems having 0 at z and 1 by z star have same magnitude response. Okay, similarly, the systems having poles at z and 1 by z star have same magnitude response. Okay, as we have seen before, if we have poles here, okay, having poles here, okay, so they have same magnitude response. Okay, so for a given system, okay, 0 pairs, okay, z naught and 1 by z naught star, okay, p naught and 1 by p naught star. Okay, if it is p naught, okay, already if you have a at conjugate p naught star, okay, then 1 by p naught. Okay, all these pairs will have, okay, same magnitude response. Okay, you can either select from here or select from here. You will have actually same magnitude response. Okay, so now how many possible systems I can design with given this pole zero plot? Okay, if I give only these, sorry, These are the zeros, right? Okay. So for the given pole zero plot, how many possibilities are there? If we ask, then there are actually, say, you can select having, say, z naught, h of z, h1 of z, having z naught, p naught, and p naught star. Okay, one possibility. h2 of z, as we have seen, 1 by z naught star, okay, 1 by p naught star, and 1 by p naught. This is another possibility. Okay, and h3 of z, okay, you can consider z naught, okay, 1 by p naught star and 1 by p naught. Okay, this also will have same magnitude response. Okay, because you are selecting from this z, and h4 of z, we are selecting 1 by z naught star comma p naught comma p naught star. Okay, so like this, there are each of the several combinations which gives the same magnitude response, especially for a given pole 0 and 1 pole. Okay, you will have 4 combinations, because here poles for a system having real quotients, they will occur at complex conjugate locations. Okay, these two come as a pair. Okay, so if you consider only real quotients, these two come as a pair. So we can't separate the pole having p naught and p naught star. Okay, but however, if you separate them, there is still a possibility to have it. Okay, the more combinations with real quotients. These are the possible combinations. Okay, so now among all these possibilities, okay, all these possibilities having same magnitude response, okay, have same magnitude response, which is the preferred system? Okay, which system do we prefer for practical applications? The one which is causal and stable is preferred, as we know, but which is having causal and stable inverse is preferred. Okay, the system having causal and stable nature and inverse also being causal and stable is preferred among all these possibilities. Okay, but which is preferred? With causal and stable nature and having causal and stable inverse system is preferred. That implies which is preferred now? The minimum phase system is preferred. Okay, among all this, the minimum phase system is preferred. Okay, so now let us see quickly how to decompose any of the system in terms of the minimum phase system. See, in some of the practical applications, you may not directly get a minimum phase system. So assume that I have a minimum phase system like this. Oh, I have a system like this. See, is this a minimum phase system? Say, even if I say that h of z is causal, and stable, okay, that means ROC for this system h of z is moderate greater than half. The question is, okay, is this a minimum phase system? The answer is no. Why? The reason is hi of z if I write now, which is equal to 1 minus half z inverse. Okay, 1 minus 2 z inverse. As we have seen before, the ROC, possible ROCs for this is mod z greater than 2. Okay, or mod z less than 2. Okay, of hi of z. In this case, it is causal, not stable. Okay, in this case, it is stable, not causal. Okay, so that implies it doesn't have stable and causal inverse. So inverse system is not minimum phase. And hence h of z itself is not a minimum phase system. Okay, because the definition of minimum phase system is that h of z and hi of z both has to be causal and stable. Okay, so now let us see, if given this h of z, can I decompose this h of z? Okay, given this h of z, can I decompose this h of z into minimum phase system? Because we have seen that for the same magnitude response, we can find more than 2 systems or more systems having same magnitude response. So given that understanding, can I decompose this into minimum phase and some other system? Okay, some some other residual system. Okay, but the magnitude response has to be same. As you can see, among all these systems, which is the minimum phase system? Say for the given definition of the poles and zeros, okay, you can see that which is the minimum phase system. So this is the minimum phase system. Okay, is this. Okay, because that not all poles and zeros are inside and its inverse is also inside. Okay, but remaining are not minimum phase. So see, I want a magnitude response to be preserved with h of z, but still, so this is not minimum phase. Okay, and this is, I want to write in terms of a minimum phase system, but have same magnitude response. Okay, so if I preserve the magnitude response here, and this also should have same magnitude response. Okay, this also should have same magnitude response as h minimum of z. Then what should be the magnitude response of this h of z? It has to be 1 for all z or 1 for all omega. Then thus it has to be a alpha system. Okay, so you can we decompose any of the system which is non-minimum phase, okay, to a minimum phase and unit magnitude like the alpha system having same magnitude response. That is one magnitude response for all. Mod HAP of Z is equal to 1 for all omega. Okay, can we have this? So let us now put these things in frequency domain, DTFT as well. Okay, any general. Okay, is equal to H minimum phase into H alphas. Sorry. Minimum phase into H alpha of e power j omega. Okay, can we decompose? Is the question. Okay, if we can decompose, then what is the advantage? We can always write the equivalent, say, for any given h of z. Okay, even if I am given with this h of z, I can write this and say that I have an equivalent system having same magnitude response and have the feature of minimum phase. That is causal and inverse, like causal and stable, and inverse also has causal and stable. Okay, given this, given we can find out this. Can we find out this? Okay, and also write H2 of Z as a function of so H1 of Z into an alpha system. That's our question now. Okay, so now let us take this example. So what I'm trying to write is, say H of Z now is given. Okay, but this, let us write only the say 1 minus 2 Z inverse, which is the term which doesn't like whose poles or zeros are inside the unit circle. Let us write this side. Okay, and which are not, let us write this side. Okay, so this doesn't disrupt the minimum phase structure. Okay, and now for an all pass system. Okay, so what do we have? So the general structure of an all pass system, H all pass of e power j omega or H all pass of Z is what? Z star minus C star, Z inverse minus C star by 1 minus C Z inverse. Okay, so here we have already have 1 minus half into Z inverse. Okay, let this be C. So the numerator term I can write is equal to 1 minus half. Okay, this is now an alpha system. Okay, sorry, 1 minute. Let us write the reverse. So bring the terms which are like which are minimum phase this side, that is which are less than, whose zeros are less than here, and let doesn't matter, but let us write this. The other ones which are two genders. Okay, for this let us write the all pass structure and let this be equivalent to, so let us bring the terms to make this minimum phase. See, to get this all pass, what do we need? Say I can equivalently write this as all pass if I take 2 out. Okay, so let us write this as half minus Z inverse. Okay, write the numerator term. Okay, just like the all pass term I have here. Okay, and the denominator term I can write it as simply like this, right? So I have just taken 2 out from the numerator and written this. Okay, and I have made this now all pass structure. Okay, and hence since I divided here, I can use this as multiplication here because I don't want to disturb the system I am writing H of J. Okay, now you can see that this can be written as, the first one what we have is all pass, and second one what we have is minimum phase. Okay, since minimum phase doesn't have any constraint on the magnitude to be 1, let us absorb this 2 also here, and hence we can write the all pass as 1 minus 2 half minus Z inverse by 1 minus half Z inverse into the minimum phase as 2 into Okay, so we have taken here a trivial example wherein the minimum phase all became 1 itself. Okay, numerator and denominator are same. Now let us take another example to demonstrate this. But the discussion here indicates that we can decompose any system into an all pass and minimum phase. Okay, let us take a slightly different example, not to clearly see this. Let h of z is equal to 1 plus 3z inverse by 1 plus half z inverse. So the question here is given h of z. Okay, it's not minimum phase, non-minimum phase h of z. Okay, decompose this into all pass and minimum phase systems. Okay, so how do we write h of z? We want to write h all pass of z, okay, and h minimum phase of z. Let us follow this sequence. To write h all pass of z, what we take is 1 plus 3z inverse, but take 3 outside to have the structure of all pass by what is structure of all pass? h ap of z is equal to z inverse minus c star by 1 minus c z inverse. Okay, so here this by 1 plus, because z inverse is equal to here minus c star is equal to 1 by 3 or c equal to minus 1 by 3. Okay, so 1 by 3 z inverse. So we have written now in all pass structure. So 1 plus, after taking 3 out, okay, we have written the denominator exactly that result in an all pass system. Okay, based on numerator, I have written the denominator. Okay, it's not there in the original system, but I have written based on the numerator to construct an all pass structure. Okay, and then what will happen? The same, this new denominator is the additional term that has come here. So I will write 1 plus half z inverse. Okay, so now you can see that this first term is all pass. Okay, I will write now separately. Okay, into second term is minimum phase. This whole thing is minimum phase. And this first term is all pass. And this is h of z. h of z is, okay, which is equal to 1 plus 3z inverse by 1 plus half z inverse. What is the benefit of this decomposition? This non-minimum phase system. Okay, but having same magnitude response as h minimum phase. Okay, both of these have same magnitude response. Okay, but this h minimum phase will enable us to design a system that has same magnitude response of this h of z, but different frequency phase response. Okay, and the phase response is determined by this all pass filter. All pass filter only has the some contribution in the phase response, but the magnitude response of this all pass system is 1. Okay, so the advantage is that what we are able to see is, okay, so h minimum phase of z, okay, enable us to replace design of h of z with stable and causal, okay, system design, and inverse stable and causal, Okay, having same magnitude response as what? As h of j. Okay, that is the advantage of this decomposition. Okay, so I will give you one example for your exercise. Okay, and then I will move on to like what will happen in the phase response. Okay, we have seen when I do this decomposition, the advantage is that they both have same magnitude response, but this is causal and stable and has causal and stable inverse, and benefit and hence replace in all practical applications for this one. Good replacement for this one. Okay. However, does it affect the phase response of the system compared to the system, or is this has even desirable phase responses or not? That we will see in the subsequent discussion. So now, yeah, I will just give you some small question for you to exercise and find out the equivalent minimum phase all pass decomposition. I am giving you the h of z. Find the minimum phase all pass decomposition yourself. Okay. Okay, fine. Now for this, suggest you to find, decompose this h of z to h minimum phase into h all pass of z. Okay, or find corresponding minimum phase system having same magnitude response as h of z. Okay, please take it as an exercise for you. Okay, right. So we will discuss very briefly what will happen to the phase, like some phase of this decomposition, effect of phase on this decomposition. Also see some properties of minimum phase systems. Okay, so h of z is equal to h all pass of z. So let us write in terms of e power j omega for simplicity. H of e power j omega. Now we are writing as h all pass e power j omega into h minimum phase of h of e power j omega. See, as we have seen, angle of h of e power j omega, now if I write, is equal to angle of h all pass of e power j omega plus angle of h minimum phase of e power j omega, right? Because these are product here. Okay, and hence, see what will happen now. As we have seen, angle of h of e power j omega, angle of all pass, h all pass of e power j omega is always less than 0 for stable all pass. Okay, is always less than 0 for causal all pass system. See, anyway, we understand that H minimum phase is causal and stable. Okay, there should be some overlapping region to find out this. So H all pass is also causal. Okay, and hence this is always less than 0. It implies that, say, among all these systems having same magnitude response, that is h of e power j omega, minimum phase system now will have maximum phase. Okay, that means this implies that angle of h minimum phase of z e power j omega is greater than h of e power j omega with same magnitude response as h minimum of e power j omega, right? So it means that among all the systems having same magnitude response, the minimum phase system has the the maximum phase or minimum phase lag. See, phase lag means phase with negative direction. Okay, is phase lag. Maximum phase means the phase being higher indicates that the phase lag is less. Okay, so maximum phase so in some sense imply minimum phase lag or phase like with negative sign, phase and proportional to minus of phase lag. Okay, so thus the name minimum phase has come based on the minimum phase lag property of these minimum phase systems. Okay, among all the systems having same magnitude response. So it's not the minimum phase but the minimum phase lag. Okay, that implies minimum phase systems have minimum phase lag or maximum phase among all the systems having same magnitude response. Okay, this is one of the very important property of minimum phase systems. Okay, so minimum phase systems has minimum phase lag or maximum phase among all the systems having same magnitude response. And this is also important. Okay, so if there are six possibilities, among the six, this will have the minimum phase lag or maximum phase. Okay, so phi minimum of e power j omega is greater than phi of e power j omega with all the systems having same magnitude response. Okay, right. So now let us, in terms of group delay, now if we see, what do you think will happen? So this is property 2. See, as we know, if you want to write the group delay, tau of omega, okay, is equal to minus d by d phi d omega of phi omega. We have seen that the group delay and phase are related and both are angular quantities, and hence the h of e power j omega, when we write, it is equal to h minimum of e power j omega into h alphas of e power j omega. We can write the tau of omega group delay of this is equal to group delay of this plus group delay of this. Okay, this implies that, but however we have written, okay, we have seen that alpha system has, okay, group delay of the alpha system is always greater than 0 for causal alphas. Okay, so because the causality is ensured because of this multiplication and overlap with the minimum phase system. Okay, and hence you can see that this this implies, okay, tau omega, tau minimum phase system has least group delay among all systems, okay, having same magnitude response. Okay, So like always, this implies that tau minimum of omega is always less than tau of omega. Okay, having systems with all same magnitude response. Okay, so this is the next property. There is another property that's referred to as minimum energy delay. Of minimum phase systems. Okay, so what does this tells is, see, how do we characterize the energy of a system? So if you in fact minus infinity to infinity, for a causal systems it's starts from 0 and 0 to infinity. Okay, this is the energy of the system. Okay, energy of the system. Okay, so this is how we define the energy. And now how do we characterize, say if we assume that there are m quotients like in the impulse response, and hence energy of the system is defined as sigma n equal to 0 for causal system. This is what we are defining here is for causal system. That's why it is starting from 0. Okay, n equal to 0 to m. With m, assume that it's finite, h of n whole square. Okay, and this what does minimum energy delay property says is energy of minimum phase system, okay, for a given m quotients, okay, will always be greater than energy of any other system having same magnitude response for the given same number of quotients. Okay, if we define for m quotients the energy of a system as like this, 0 to m h of n whole square. Okay, m can go to infinity if there are infinite number of things, but we are looking only up to a point m. Okay, so in a given h of n, if h of n is like this, okay, I can set my m. Okay, I may see 0, 1, 2, 3, 4, 5, 6. I can see energy up to, okay, energy only up to here. In that case, m is equal to 4. Okay, 0, 1, 2, 3. So m is 3 here. Okay, 0 to 3. Okay, that means for first 4 samples of the signal impulse response, I am looking at the energy. This is referred to as partial energy. Okay, so what it says is partial energy of a minimum phase system always is greater than partial energy of any system having same magnitude response. Okay, so this is referred to as minimum energy, like minimum energy delay property. Okay, so that means partial energy of minimum phase system for any m. Okay, m need not be a specific value. It can be any value for any m is greater than the partial energy of minimum phase system of systems, all the systems having same magnitude response. It means that if I say that the system h1 of n, okay, and a system, if I give you another h2 of n, if I say that both have same energy response, okay, so if I calculate for the minimum phase system, okay, so which is minimum phase if I ask now between these two, 0, 1, 2, 3, 4, 5, 6. Okay, between these two, if I ask which is the minimum phase system, okay, so which is the minimum phase system? Given this impulse responses, all the possible like systems with different impulse responses having same magnitude response, say H2 of n can be minimum phase is minimum phase. Okay, if there are only two things, is minimum phase, not H1 of n, because if I see that, okay, so the value of this for any m is higher than the partial energy defined as summation H minimum of minimum phase impulse response whole square, because this can be complex quantity n equal to 0 to m is always greater than or equal to summation h of n whole square n equal to 0 to m. Okay, now having same magnitude response. As h minimum of n. Okay, for all n. Okay, this is valid for all n. So this also indicates that h minimum of 0 is greater than h of 0. Okay, that means the first sample at 0 will also be greater than the like highest for minimum phase systems. Just by comparing the, so if the sample at zeros are different, the sample value at the 0 is different. Just by comparing this, you can tell which is the minimum phase system. Okay, this is property 4. This you can consider as property 4. Okay, that means 0th sample for the minimum phase system is greater than h of 0. This also having same magnitude response. So system having same magnitude response. This you can easily derive from the discrete time Fourier transform expression. Okay, take it as the exercise. Okay, so because of all these desirable properties, minimum phase system is well used in many of the practical applications, and that replacing the original system that is given. Okay, and this all pass minimum phase decomposition will enable us to do that effectively. Thank you. You can see that for any of the system you can find all pass minimum phase decomposition, and the minimum phase system corresponding to the that decomposition gives exactly same magnitude response as that of the original system, and it has the properties of like causal stable inverse, also minimum group delay, minimum phase lag, maximum phase, minimum energy delay, and maximum sample at the 0th location of its impulse response. Thank you.